Good afternoon, everybody. Thanks for sticking around to the conference, giving us the opportunity to talk to you about a few defenses that we've developed to protect against cold boot attacks. I'm joined here today with Tim Hollebeek and Alice Valenkin. I'm Patrick McGregor. We work at BitArmor, which is a software innovator that leverages encryption in unique ways to provide lots of new benefits with respect to data protection as well as distributed data management. Two of us actually did graduate work at Princeton. And in terms of what we're going to talk about today, we'll just give you a brief overview of what the full disk encryption market looks like, why people are buying, and how many companies have deployed full disk encryption to protect their sensitive information assets. Then, just to make sure that everybody's on the same page, although some of you may be very familiar with how cold boot attacks work, we're going to give you an overview of the mechanics of a cold boot attack, and also demonstrate to you that cold boot attacks are a lot easier to achieve than many people think. And then we're going to present four software-based defenses that we've developed that address different cold boot attack scenarios. To summarize them quickly, the first is just a method for wiping keys when a computer cleanly shuts down. And although this may seem trivial, it's actually difficult to do with respect to full disk encryption systems. Leveraging built-in temperature monitors that exist in most laptops and desktops to detect if cooling is occurring, which could indicate a cold boot attack is in progress. Taking advantage of some hardwired behavior with respect to memory systems that allows us to securely erase keys before operating systems can be booted to look at them. And then a rather intricate defense that protects against the most aggressive cold boot attacks that effectively creates a virtual piece of hardware within the computing device to protect keys against any sort of the cold boot attack scenarios that were described in the Princeton paper. And then we'll conclude with some thoughts for the future and things that we can do to prevent cold boot, the next generation of cold boot attacks. Okay, so what is full disk encryption? Quite simply, a full disk encryption solution is a software or hardware component that effectively encrypts every bit of information on a drive or a drive volume. It's most often deployed to protect laptops or mobile devices for obvious reasons because they have the highest probability of being stolen or being targeted for theft. And most encryption systems use pretty vanilla crypto to actually provide the protection. They use the industry standards that we know and love, such as AES and DES. But often the security of the encryption is fundamentally based on a very simple authentication mechanism, which is most often a simple password. The password can be used to derive or potentially unlock a key that's used to encrypt an entire disk volume using a standard mode of operation, such as CBC or something that's slightly more exotic. You see stronger authentication systems that often involve maybe a USB token to supplement the password, but it's also a fact that lots of companies actually deploy full disk encryption without any passwords at all, and that's a completely different matter. But in general, the security can vary significantly between FDE implementations. But I guess the most important performance consideration is that since you're encrypting all disk activity, it's very important that you be able to provide the encryption service in real time. So let me describe how disk encryption is most often implemented. And this is a software representation of how it would be implemented, say, for a Windows-based machine. Essentially, applications make calls to the file system as they normally would, do reads, writes, opens, closes. And then a file system filter driver is implemented by the FDE vendor, which you can think of as being a wrapper around the file system or an underlying storage device driver. Allows you to intercept every file system read-write request, which is often done on a sector level or, say, a page level of 4 kilobytes, and then perform fast encryption or decryption for the application that's requesting it. Since there's so much file system activity, though, through booting, through normal usage, and you can sit and stare at your laptop hard disk encryption or hard disk light to see how much activity is really going on, it's a fact that encryption keys have to be kept perpetually in memory. It's not really feasible for you to ask a user to authenticate himself or herself every single time they want to encrypt a sector. So one of the design considerations that we have to think about when we're trying to defend against cold boot attacks is that we can't safely tuck away keys for some periods of time. We have to assume that they are always available in memory. So why are people buying full disk encryption today? Quite simply to mitigate risk. They reduce a chance of being sued, being fined, or, of course, losing some sort of sensitive intellectual property. It's a fact that a single data breach can cost a company between $90 and $305 per record. And a record might mean a single Social Security number. So if you do some simple math and say you lose a spreadsheet on a laptop with 50,000 Social Security numbers in the spreadsheet, you're talking about millions of dollars in both direct and indirect losses. The average cost is about $4.8 million per company incident. But most people don't buy encryption to do the right thing. They don't necessarily think ahead to encrypt their laptops. The industry hasn't evolved to that point yet. So most often people buy encryption as a reaction to a breach that has occurred, or to proactively address some compliance issue or breach notification issue. So there are tons of regulations that apply to pretty much every industry and government agency that basically say thou shalt encrypt, and that's generating a huge amount of activity in the space. But in the private sector, encryption may often be purchased to avoid breach notification requirements. So there are laws in nearly every state now that require you, if you say lose a laptop or something else like a backup tape with sensitive information on it, that you have to inform the public. And so we've all probably received a letter from a bank or financial services institution that has lost something, and they're informing us that our information may have been compromised. When that sort of event happens, it leads to real significant costs for companies. Ranging from having to pay for credit monitoring services through lawsuits that are applied, and also through lost customer business. But in pretty much every single one of these laws, there's actually a provision that allows you to get out of jail free or not have to notify the public if you have encryption deployed. So oftentimes, people are buying encryption not really for security, but just to get out of this notification requirement. So how widely is FDE deployed? At the end of 2007, nationally across all companies, about 20 companies had deployed full disk encryption to protect at least some of their laptops, which again is the most common application. And based on some of analyst estimates, at the end of 2007, in 2007 alone, over $200 million worth of business had been done in selling full disk encryption solutions to companies and government agencies. It's expected that over time, the total market potential for existing full disk encryption solutions is going to exceed $1 billion. But as we've learned through these recent cold boot attacks that were released by the Princeton folks, all of this investment that has been made, and it's again on the order of hundreds of millions of dollars, may be completely at risk. So at this point, I'm going to turn it over to Tim Hullabeek, who's going to talk to us about how cold boots attack work.
Okay. Does there actually happen to be anybody from the Princeton team in the audience, just real quick? In case any of you end up watching later, we did notice you won the pony for it last night, and congratulations, very well deserved. We're actually big fans of this stuff, and that's why we started looking into what we could do about this. I'm sure all of you out there are familiar with cold boot attacks, but in order to talk about them, we're going to have to dissect them, take them apart. So we're going to talk in fairly specific detail about each tiny little component, and hopefully that will give us an opportunity to show you exactly where our defenses fit in. And one of the nice things about our software defenses is each of them addresses certain threats and certain attack scenarios. There are a lot of ways you can put together a cold boot attack. But together they provide a much more sophisticated defense. Some of the scariest attacks are extremely simple, but relatively simple to defend against. But on the other hand, you can think up some fairly complicated attack scenarios, and defending against them is very, very hard. So we'll be presenting 4 software-only defenses, and together they provide a comprehensive defense against cold boot attacks. To summarize what we've said so far, the security of the data on your hard disk depends on the hard disk encryption key. And this key is unlocked during pre-boot authentication, making it a very, very attractive target. Standard PC memory is generally thought of as a temporary storage mechanism. And the model that everybody has in their head is, when it's powered, it's got its data. When it's unpowered, the data disappears. And that's a nice model when you're trying to think about how to program a computer, but unfortunately, it's not true. And what's a very common theme in security is people build systems based on the simple models they have because they're building complex systems. You can't think of the complexity of all the parts. You put together things based on simple models. When the simple models don't correspond to reality, reality takes you out back and starts having fun with you. And so the problem is, this is not true. Memory does keep its values. There are ways to make memory keep its values a lot longer than you'd think. The Princeton people managed to keep values in memory for over a couple days. This is trouble. And so basically, in certain situations, the take-home message is full disk encryption is completely broken. And, sure, there are some things you can do to defend yourself, but in many common scenarios, you're going to have some serious problems. So, yeah. What can we do about the fact that these decryption keys persist in DRAM, even after the power is lost, possibly for a long, long time? How long? Well, It depends. In some cases, it's only seconds. And the modern laptops that we tried, especially without cooling, it's 3 or 4 seconds. Can be substantially longer on old hardware. If you go back to laptops that are in the 1999 to 2003 range, you'll see some examples in the Princeton paper where even without cooling, they're holding their values for minutes. Now, right. Okay, so there are a couple annoying things when you're trying to implement these. Some machines do zero out their memory during a power on self-test. Can be disabled, often is disabled just for speed reasons. ECC memory is also a problem. One of the first times we tried this, if you have a desktop especially that was originally a developer desktop, it most likely has ECC memory. ECC memory has more values than just the data bits. If you actually accessed ECC memory where the data had decayed, you would get a memory error. So because of this, computers that use ECC memory go ahead and zero out the memory before they allow you to access it. So the problem is many cheaper systems do not use ECC memory. Most laptops do not use ECC memory. So in the real world, that's not necessarily a solution. The OS does not assume memory contains zeros. They initialize it for you, and basically they're very friendly. They provide the illusion that you were expecting that memory contains zeros. If the attacker boots to his own custom bootloader, he is under no obligation to provide the same illusion to himself. So your custom bootloader can overwrite just a teeny part of memory, go on, read the rest. So that's what you do. You boot to an alternative operating system. And this is the only thing this is the only real necessary component of this attack. And what you do is you just go in, record all the memory. The bootloader, essentially all you need, you got BIOS support for I/O. You have to be able to access memory. You have to be able to iterate over memory. This is a few K of code at most. The only thing you really have to work around is the fact that the computer initially comes up in 16-bit mode. You have to try to access all of extended memory. So, an alternative OSs, there are lots of ways you can boot a computer. USB, floppy, network, whatever you want. USB turns out to be a fairly fun way of doing this just because of the fact if you boot to a USB device, the BIOS will let you write back to it very, very easily. You can put a nice large partition on a 1 gigabyte USB device, suck all the memory down onto the USB device. Downside is USB is a little bit slow. It takes about 10 minutes if you're doing it USB. But if you're a little bit more sophisticated, well, there's no reason why you can't shut off the power, pull the chips out of the computer, transfer them to another computer. That computer can be set up any way you want. You can already have the power on self-test disabled. You can make sure it doesn't have a BIOS password. You can make sure it has a nice spare hard drive that you can write the memory onto really, really fast. You can make sure it doesn't have any ECB support. If you actually take ECB memory and put it into a non-ECB computer, it's going to run like non-ECB memory, and you get right around that problem. And the most annoying thing about this that actually isn't mentioned in the Princeton paper, if you walk up to an arbitrary laptop and you attempt to boot to an alternative operating system, of the 4 laptops we attempted to do this with, none of them used the same key for selecting alternative boot options. It might be F9, it might be F12, it might be escape. Who knows? And you get about 2 seconds to try. And if you don't get it fast enough, it continues booting to the operating system and it starts wiping all of the memory you wanted to have fun with. So, another thing that people have said is, well, I always shut my computer down before I go through the security terminals. My computer's never on. My computer's never sleeping. My computer's never hibernating. How could somebody get to it right after I shut it down? And, well, some of that's a little bit true. A lot of that is people are in denial. And even if we went out, we took a survey. Surveys are notorious for people are going to tell you what you want to hear. But even in this case, 40% of users admit that while they're wandering through the airport, they're traveling, they're in a car, they leave their laptops in sleep or hibernation mode. And one of the dirty little truths about FDE products out there is many of them do not support hibernation all that well. Hibernation comes up a lot slower due to the fact that due to the way operating system boot works, it's hard to get FDE to have hibernation support and do it quickly. Some of them do not support hibernation at all. Some people are just lazy and like their computers to come up real fast, so they always sleep them instead of hibernate. It doesn't really make your battery last that much less. So, and worst of all, there's no real difference between technical users and business users. Everybody just sleeps their laptops. So, and the problem is, a sleeping laptop is a vulnerable laptop because you don't have to re-authenticate. Another reason FDE people tend to sleep their laptops, if you hibernate your laptop, it's powered down. If you want to use it again, you have to re-authenticate. Nobody likes re-authenticating. So anyway, the other problem is desktops matter too. If you're sitting in an office, you walk away from your computer, sure, you got the auto screen lock. That's helpful in a lot of scenarios, but somebody can walk right up, cold boot that desktop as well. So that's an important attack scenario too. And one of the really annoying things that we have to remember when trying to implement these attacks is the Princeton results on key reconstruction are really, really good. Some of the bits start decaying pretty soon, but because of redundancies in AES key schedules, one of the AES keys is exactly the full key, but then you have 9 more copies that are essentially very closely related to the full key. It doesn't take very long to figure out, even if you've got a fairly corrupt version of the key schedule, to figure out what the real key schedule actually is. And especially since modern computers are fast. You can search if you don't know quite which key it is, and there are millions of possibilities. Millions is a small number. So basically, because of the way that because of the efficiency, because of the fact that they can reconstruct these key schedules very well, because of the fact that these key schedules are very easy to recognize in memory, the Princeton people didn't even have to understand where the FDE vendors were storing their keys in memory. They could just search through, find an AES key schedule, reverse engineer it, get the disk key. So this is scary. If you're trying to design a defense against this, they can get away with tolerating 25% errors. This is not very good. So we got to find something that can do a lot better than this. Okay, now, again, hammering home the point that it's very easy to do this, we're going to show you 2 scenarios. In the first scenario, it's actually easier, it takes less time to carry it out than it takes to describe it. Oops, here it is. So the first scenario is you just walk up. All you have is you get a custom USB device. You find this laptop that's sleeping or sitting in screen lock mode. Put it in, press the right keys, memory starts dumping. 10 minutes later, you're done. And now, let's say you're lazy. You don't want to implement an alternative operating system to boot to. Well, you're lucky. There are already 2 versions out there on the internet that you can download and give you instructions for setting up these USB keys. Now, if you want something a little bit more advanced, well, then you have to go ahead and cool the memory. But, if you watch, this isn't really that hard either. All you need is a screwdriver, a can of compressed air, and a little bit of technical savvy. If you watch, all you got to do is take this thing, shake it a bit, turn it upside down, and what ends up comes out at about minus 40 degrees Celsius. And if you watch, the temperature drops in under a second. So now, as you're doing this, one of the defenses we talked about, of course, is those are the sensors that are integrated in the motherboard right next to the memory to make sure that your laptop isn't overheating. Guess what you should be doing if you see the temperature going down to minus 40 degrees real fast? So there you go. You see the laptop memory ends up being rather frosty. The memory will actually persist even without sitting there and freezing it. It will persist for a good 10, 15 seconds to a minute or so at well below 0 Celsius. And then so you have plenty of time to, what do you want to do? You want to just reboot it so that you get very, very few errors, somewhere on the few hundred bits flipping in a million. Remember, 25% you can reconstruct the keys. Here's the memory getting dumped off. Yeah, this is not an attack you want to see. So anyway, now I'm going to hand it off to Alex, and he's going to describe the first few of our software defenses that prevent cold boot attacks from working.
Okay, thanks, Tim. All right, so you already heard how easy it is to implement certain attacks, cold boot attacks on laptops, on computer memory. Attackers use multiple techniques as you know, to attack these machines. Hence, there is no silver bullet really against this attack, especially if you want to implement a defense just using software. Of course, there are possibilities to create hardware solutions, but of course there are limitations. Not everybody would like to replace their laptop, would like to replace their desktop in order to be protected against cold boot attacks. So what we propose is a set of defenses against these attacks. Only software-only defenses, no special hardware is required. These defenses have their advantages. They also have their limitations. However, if all of them are implemented on a single system, they create a complete defense system against a number of most feasible cold boot attack scenarios. So, what we are going to talk about today is the 4 defenses. I will start with the first few, but before I do so, I would like to introduce certain attack vectors or certain attack scenarios that each of these defenses will be applicable to. So, the defenses address scenarios where computers are physically stolen. So, first of all, we assume the computer is in the hands of the attacker. The computer is in the hands of the attacker shortly after it's been shut down by the user or by the owner. The computer is stolen while it's hibernating. Now, this is not to be confused with the computer in the hibernation mode, but it's actually going into hibernation. Assume also the cases where the computer is in sleep mode or the computer is locked down. Okay, so the first technique deals with the very first 2 attack cases, where the computer is shut down recently and the attacker got a hold of it, or the computer is entering the hibernation mode. Now, if you think about what's going on when the computer is actually going into hibernation. So, imagine an FDE machine. The FDE machine, when the owner of the machine started using it at some point in time, it turned it on, it completed the authentication. The keys are stored in memory for further encryption and decryption purposes. Perhaps the entire key schedule is stored if it's AES encryption, perhaps. And the keys are there all the time in memory until the machine actually shuts down. The reason for this is because, first of all, recomputing the key schedule for every single I/O operation is very expensive. If we were to, at any point in time when the computer is running, if we were to delete the keys and not recompute them, the machine will essentially blue screen, because for any single I/O operation, disk I/O operation, you would need to have the key to either encrypt the data and put it on the disk, or decrypt the data when the request for data read comes in. So, in this case, computer is entering the hibernation mode. The keys are still in memory. The attacker will get the computer. The computer is shutting down. Computer will probably already shut down by the time the hibernation is complete, but the keys are still in memory, since we have that remanence issue. Okay, so the natural way of thinking how to fix this problem is to not keep the keys in the memory. Of course, we've got a problem because you can't really you can't really delete them unless you want the machine to blue screen. You cannot come up with an idea that that would put the usability in jeopardy, because if the user continuously sees the machine blue screen every now and then, this is going to be a problem. So this is what actually Princeton paper mentions in details, because it's difficult to delete the keys from memory just in time. You must delete it just in time before the machine shuts down. So what we do is we propose a simple more or less simple OS-driven solution, which works at least on Windows operating systems. So essentially, the outline of this is we want to prevent the key material from being available after shutdown or hibernation. The machine must be cleanly shut down at this point. You see, if the machine cord is pulled or the battery is removed from the laptop, there is really nothing we can do. We cannot detect that the attacker is trying to pull the battery out, so you cannot really do that. So we assume that the machine is cleanly shut down. And again, this works through Windows operating system standard mechanisms. So let's take a look at this diagram. The diagram actually shows how shows the entire cycle of machine shutting down. So there are 5 states that the machine goes through. The very first state is the machine working in the working condition, in the working state. So S0 you see there. Now the machine is entering sleeping or hibernation mode. It must go through a number of states. It must enter the first state. The first state assumes says that the video is going to be shutting down now. Then the sleep state, number 2, which says perhaps that some other system operation components are shutting down, and so on and so on. So this goes on until essentially it enters sleep state 4, at which point disk I/O is actually shutting down. So at S5, at state S5, the machine is shut down. There is no way to reverse these states. So you cannot stop executing the shutdown mechanism at some point and come back to the machine, to the working machine. You can only go one way. And one way is to shut down the machine, and then if you want to have it running again, you have to power it up, go through authentication procedure, get it running again. So what we can do is we can actually have, if we could have notification in between the states 4 and state 5, right before we know that the disk I/O is shut down and there is no more disk operations are coming forward, then we can at this point securely delete the keys from memory and proceed with the rest of the hibernation procedure or shutdown procedure. Again, the keys are removed in order for the machine to be running again. You start it up again. If you are a legitimate user, you can go through standard authentication procedures. You get your keys back, and the machine is running again. All right. So the implementation of this approach is basically through the filter driver. We already have a filter driver. Since this is an FDE solution, full disk encryption solution, you already have a filter driver that actually handles encryption and decryption of I/O requests for you. So all you really have to do is to instrument this driver to actually handle power state ERPs and recognize when the machine is about to enter the state 5. Once the machine enters state 5, you command the driver to erase keys and key schedules securely from memory, and you are done. Basically, you release the ERP, system continues with the shutdown, you're all set. Once you boot up, you enter the authentication, you go through the authentication procedure, and machine is up and running again. Again, this will work for pretty much all modern Windows operating systems, starting with Windows 2000 and all the way to Server 2008. Okay. Now, this approach had its limitations. Like I already said, the machine must be cleanly shut down. If the attacker possesses the machine and pulls the plug, removes the battery, there is no way for the driver to actually know that the machine is shutting down. There is no way for the driver to delete the keys and clean up the memory. So we must consider other attack cases, other attack vectors, and come up with other approaches that would defend against those. So we've got two more significant cases where the machine is, three more attack scenarios where the attacker would try to cool the RAM before the power loss and would attempt to transfer the memory over to his own machine. He might attempt to boot to an alternative operating system, either remote or local. He doesn't have to transfer the RAM at that time. Or he can try to cool the RAM down immediately after power loss and transfer the memory while it's called to a different machine. Again, these other approaches will relate to machine being in sleep mode or when the machine is locked, as a screen lock. Okay, so consider the first out of the three remaining attack vectors. So the attacker, again, has the machine, cools down RAM, while the machine is still hot, and with the purpose of transferring the RAM over to his own machine and do the memory dump. So once again, the machine is hot, meaning that the keys are still in memory. The juices are essentially still flowing through the circuits, meaning that the keys are going to be there until he decides to power it down. He would try to cool the RAM down, thus preserving the memory state and delaying the memory decay, data loss, and transfer memory over to a different machine. Again, what would be a natural way of thinking of trying to, how would you defend against this attack? The machine is still not an attacker's machine. It's an owner's machine, although the attacker possesses it. So it's our code still running there. Now, you would hope that if you could only know that the cool down process is happening and you could delete the keys at that time, you could probably have a good chance of saving the data. This might, of course, even if you attempt this may cause the machine to blue screen immediately afterwards if you delete the keys. But if you see that the temperature of the machine drops to negative 50 degrees Celsius, there is a good chance that this is not owner traveling through North Pole. So. Princeton paper, of course, mentions things like hardware sensors introduced to a system, and polling these sensors would help detecting an attack like this. But again, the limitation is you would have to have a specialized hardware, and we tried to avoid that. But we really don't need to use the temperature sensors. That would be specially built for this solution. In fact, all modern motherboards and desktops and laptops have temperature sensors built in. I can guarantee you that the laptops that you have, those of you who have laptops today in this room, each laptop has at least 4 temperature sensors built in various places on its motherboard and in other components. Same with the motherboards of the desktops. Now let's talk briefly about cooling down memory. Okay, so this can be actually accomplished, of course, in 3 ways. In natural cool down, so once you shut down the machine, the temperature is going to naturally go down unless it's in a hot oven. You can also use aerosol canisters, like we've shown in the video. Just turn it over, cool it down a little bit. As you can see, as a matter of fact, on this picture, this is about, probably less than 2 minutes of cooling down RAM on this desktop. This brought the temperature immediately down to negative 30 degrees Celsius. So the temperature that you can get the temperature that you can get with the aerosol canister is probably as low as negative 50. You can go even further and cool it down with liquid nitrogen. This is going to give you negative 200 degrees Celsius, and the machine can be at this state, or the memory can be at this state as long as you have liquid nitrogen. And by the way, with the aerosol canisters, the temperature will be, if you stop applying the gas, the temperature will remain at this state for about, well, it will start heating up again, but you will have at least a few seconds of that same temperature sitting at the negative numbers below freezing. So this is applying that same aerosol canister gas over probably few seconds, 5 seconds perhaps, something like that. So, and this is, by the way, the working system. This is a live system. It's still working. It's still doing some operations, showing. It's actually, I had Windows, some flavor of Windows running on this system, and it was just working fine. Now you can ask, what happens to this? What happens to the motherboard? Why, and why it's still running? Essentially, the gas that flows through is non-conductive, so this is not going to cause much problem. Of course, you may ask, what happens with all that ice that would essentially melt? Yes, it will, and it will melt into water, but the motherboards usually, and if not all of them, have a protective film these days on the board. And well, our experiments shown that nothing really happened even after this ice turns into water. So this is as real as it can get. Now let's talk about temperature detection. Modern motherboards, again, have the temperature sensors built in. They are built in for heat control, essentially. This is how they control the airflow through the fans. Sensor data is readily available for these sensors from the either operating system or the BIOS. Sensitive decryption keys can be erased by the software when extreme drop in temperature for M zone is detected. Let's take a closer look at the sensors. This is a layout of a typical motherboard. You can see a CPU socket there. There is a temperature sensor on the CPU, of course. There is a temperature sensor right next to the CPU in this dot or square dot zone there. Then you start with the memory modules. You see 4 of them. This is actually the same motherboard that I tried to cool down in that previous slide. The temperature sensor is very conveniently located right in the middle between the two memory chips, basically measuring the temperature. Now the question is, now we have temperature sensors, we know that they're there, and we can actually attempt to use them. The question now is how reliable they are. I mean, for the purposes of detection. Now, you can refer to any data sheets for these sensors that are built, that are available on motherboards. These sensors, actually, you will find that these sensors actually can detect negative temperatures down to negative 65 degrees Celsius with an accuracy of about plus minus 3 degrees. The sensors are infused in the motherboard these days. They don't really stick out, so this makes it difficult to tamper with sensors. Sensor leads are going through inside the board, because the modern motherboards are essentially 5-layer PCBs. So the leads are going all inside, going somewhere into the controller, and the controller is a system on a chip, most likely built into the south bridge, and you don't really want to mess with the south bridge unless you want the computer to die. So, and the response time is in milliseconds, so you can actually take actions immediately once you detect the problem. This is the graph of Cooling down memory and the temperature response. This is, by the way, the graph of that same machine with Windows running on it when I tried to cool the temperature down to -50, or actually -30 at this point. So you can see at the top, this is in Fahrenheit, so you can see at the top the normal operating temperature at around 80, 90 degrees probably. Then I started applying this canister gas, the difluoroethane, and the temperature immediately went down, almost immediately went down to -30 degrees Fahrenheit. Then I stopped applying it, and the temperature went up. This is what I got from the temperature sensors that are built into one of those motherboards that I had to test with. I had similar results with the laptop motherboards as well. With the laptop, it's actually even better because there are multiple sensors located in a short distance to each other, and so you can actually get readings from multiple sensors at the same time. Now, this gives you an additional assurance that this is not a false negative problem. This is not something that's going wrong with the sensor. It's actually indeed an attack. So, what we do next when we get when we know all about the sensors, we need to get the readings off of them. You can do this either through regular Windows API, thermal zone temperature API. If available, if it's not available, you can always access sensors data off of their controllers. So I2C communication through SMB bus or something like that. That should definitely work. Now, once you got the data, you analyze the drop. If it's below a certain threshold, you raise the keys. This will inevitably cause the machine to blue screen because the next I/O operation coming in will not be serviced properly, but it's a negative temperature inside the machine, and it's a probable cause. So, of course, this is not, there are more attack vectors, and therefore, we are not done yet. There are more solutions. There are more defenses. So with that said, I'm giving the microphone over to Tim again. He will be describing other defense techniques.
Okay. The next one I'm going to talk about, we're going to leave cooling for a little bit of time, although cooling actually interacts interestingly with this one. If you're booting to an alternative operating system, remember that what we want to do here, if the operating system shuts down cleanly, the keys are going to get scrubbed. So the way we're going to boot to an alternative operating system is by removing the battery, forcing the power to be off for a short period of time, plugging it back in. If you're using the Princeton techniques, you actually don't have to worry about anything more than that because you'll get a bit of decay, but you're just going to go ahead and do key reconstruction. You'll see later that with some of our other defenses, even if you're booting to an alternative operating system, you're going to want to be trying to do some cooling in order to get around some of our other tricks. But first we'll talk about booting to an alternative operating system. That's a major attack vector. What do we do about this? And the biggest problem about this one is they're cutting the power on us. The next time the power comes up, the next instructions that run is a custom bootloader. That means that the attacker's code is the next code to run. Our code never gets to run again. Okay. Our code never gets to run after the attack starts. How can there be a software-only defense against this? It turns out there's a really clever trick here that works that takes advantage of the way the BIOS boot system sequence works. And it will apply to all PC architectures and will work no matter what bootloader the attacker chooses to use or what method he uses of booting the operating system. So to give you a little bit of background, normally FDE vendors don't really pay an awful lot of attention to where they're keeping their keys in memory. They have to be in non-paged memory because obviously if your disk encryption key swaps to the disk, you're in serious trouble. But other than that, they're not really stored at any fixed virtual or physical address. And you could consider this an advantage because, hey, you have to go searching through 1 gigabyte of memory in order to find the key. But on the other hand, not only do you have as long as you want to find the memory, you also have the source code and all the intermediate data from the entire operating system. And yeah, it's not going to take you very long. And the keys have like we mentioned, they have a very easy pattern The Princeton people have automated tools that just run through memory and find them immediately. So unless you're a hardware guy, you generally don't spend much time thinking about physical addresses. The whole point of virtual memory is you don't have to worry about them. But sometimes they turn out to be really important and you can do clever things with them. So to explain how these bootloaders work, basically immediately after you cut the power, you put the power back on, the memory is still in the state it was originally, modulo a couple bits that may have flipped. But the CPU comes up in a very nostalgic configuration. It's essentially in 1980s mode. It's running 16-bit, no virtual memory, no page tables, no anything. And the other problem is it's got the BIOS, but it's going to be loading an operating system. It sort of has to have an agreed-upon set of conventions with the boot device on how we get things going. And the agreed-upon convention is that the boot device gives 512 bytes of executable data to the CPU. The CPU starts running it, and those 512 bytes contain instructions and BIOS operations that can load another additional small program. Like I mentioned, the small program can be extremely small. Because of that, the odds that it overwrites the key is really, really small. It just scans the rest of the memory, writes the data back to the boot device. All the rest of the memory is undisturbed, so you can go ahead and search for the key. So you can recover the remnants of memory with high probability unless, well, it turns out that the convention is that the BIOS boot record is always loaded at the physical address 7C00. So why don't we put our keys there? And what happens is, the next time they try to boot it, well, 512 bytes gets loaded. That overwrites all their encryption keys. Game over for the attacker. He can get all the rest of the memory he wants. He's not going to get the encryption keys. So, and the really nice thing about this is if you're doing an FDE filter driver, the vast majority of the disk is encrypted. You've got to get into the boot sequence very early anyway, because you're going to help the bootloader decrypt the rest of its memory, because the hibernation file, the bootloaders, the operating system is all on the encrypted portion of the hard drive. Well, since you're already tightly encrypted with the file system, and because you're tightly integrated with the file system, you get loaded very early, you get first dibs on which pieces of memory you want. All you have to do, there's a nice Windows function that tells you, I want a page in low memory. So unfortunately, it only takes it takes a maximum value you can handle. But you say, I can't take anything above 0x8000. And it comes back, Windows comes back and says, well, would you like 0x3000? And you say, no, give me another one. And you keep going until pretty soon Windows gives you the page that contains 0x7C00. Then you can go ahead, free the rest of the low memory pages that you don't want. You've now got 512 bytes of secure storage that nobody can access by booting to an alternative operating system. So what can you do with 512 bytes? Well, you can put lots of disk encryption keys in there. It's actually enough room for an entire AES 256 expanded key schedule. You can also play tricks with putting a master key of some sort up there that encrypts a bunch of other memory that you might want to protect. As soon as the master key gets smashed, that essentially makes the rest of the memory unretrievable. So you could actually be storing a fairly large amount of data that's not going to be accessible if somebody boots to another operating system. And since it's the BIOS that's doing this, it doesn't matter where the boot sector is coming from, USB boot, network boot, and so on. They all work exactly the same way. Doesn't matter what code the attacker writes, isn't going to change anything. When the disk encryption is destroyed by the boot process, the data is not available anymore. So basically, what this is going to force you to do, you can't boot to an alternative operating system. What are the limitations of this? Well, this is what forces you to pull the memory and put it onto another machine. Because as soon as you start pulling the memory out, the easiest way to do it is pull the memory out, move them around. Now 7C00 isn't quite where it used to be, and if you boot the machine, the keys are going to be there. If for some of the reasons we mentioned earlier, you also are using a secondary machine, well, that gets around it as well. So anyway, we've got these first three defenses. They force you to do a little bit of stuff, but there's this last one that we have that causes you severe problems. And this works even if our nightmare scenario at this point currently is the first thing you do is you cut the power so that there's no additional software defenses. Then immediately after that, you got a fraction of a second, you cool down the memory. Transfer the memory to a second computer. If you boot the computer, you can save the memory to an internal hard drive. You can even remove the hard drive from the first computer, plug it into the second computer, clone the hard drive. You've now got the memory, you got a disk image. You put the first computer back together, nobody can tell what happened, you walk off. Well, what can we do about that, especially since the memory image probably only has a few errors in a million? The Princeton paper and options mention some options, but full disk encryption, really, in your decrypt cycle, you're counting cycles. You don't have many options. But we've figured out a way of doing this that actually works. And I'm gonna let Patrick McGregor talk about this.
Memory remanence first.
Oh, yeah. Oh, yeah. Actually, that's right. First, we're going to mention a bit more about memory remanence. And the reason we mention this is because we don't actually know of any results out there, other than the Princeton results and our results, about the behavior of memory. And because of that, it's very hard. It turns out a last defense is actually tunable. And if you tell us how many bits of error you want to tolerate, we can go ahead and give you a defense that will make sure that with that many errors, the key will get destroyed. So the Princeton paper, they were interested mostly in how long does it take for a large number of bit errors to happen, because they could tolerate up to 25%. The techniques we're going to talk about, you're more interested in how long does it take to get to the first flip. Both of those numbers are not widely known, and they depend upon the bus speed that you're looking at. They appear dependent on memory density. Even with similar bus speeds and memory densities, different manufacturers seem to have different behavior. If you look at the Princeton paper, they've got some odd effects that are going on. We had one laptop that appeared to have two different populations of bits, some that decayed much faster than the others. But anyway, if you're really, really actually paranoid, one of the best ways to defend against this is memory is cheap, upgrade your RAM. The modern DRAMs decay much, much faster than the ones of 10 years ago or even 3 years ago. So for hard numbers on modern computers, 3 seconds at minus 40 degrees Celsius, this was about as quickly as we could manage to boot the machine with cooling. And this was actually a case where we continuously cooled it just to make sure it was staying at the same temperature. 512-byte memory module. We managed to get down to 0.0375% of the bits flipped, even on a modern DRAM. So that's 375 flips per million. Pretty tough to defend against exclusively in software. I should also mention we've got a really fascinating result. One of the things we decided to try is, does it matter how long the bits have been held in memory? Because one of the things you could think about doing is you could XOR your key back and forth so that the bits are flipping back and forth. We had a large section of memory that was flipping back and forth 10 times a second. We expected that what we'd see is we would just see higher bit error rates or the same bit error rates. What we saw was really weird. Portions of the memory, despite the fact that at the time the computer was shut off, it should have had uniformly one of the two values. Some of the bytes in memory had one of the values, possibly with a few errors. Some other regions had the other byte. There was no rhyme or reason to which parts of memory were keeping which value. So we have to do some more investigation, but if you're looking into defenses for this, it does look like flipping your values around in memory real quickly does provide you with some defense. So anyway, now on to the really, really fun, complicated defense.
Okay, so to frame the defense and the different aspects of the technology that we've developed, we outlined 3 key problems that we have to worry about managing these full disk encryption keys. And we touched on these throughout the presentation, but just to concisely and succinctly touch on them again. The first is the fact that attackers can get to nearly all the memory that they want to if they're performing particularly an aggressive cold boot attack. Now, we are assuming, based on our own results and the results that were in the Princeton paper, that we can count on a few of the bits flipping if you were to perform a cold boot attack, and it might be just a few per million. But for the most part, we have to assume that an attacker can get to whatever memory they want to see. The second is, as we touched on, is that we aren't able to take any shortcuts around protecting keys such that they're only available in memory for a limited period of time. It's just not realistic, and it would cause full disk encryption deployments not to work. So we have to assume that the key is perpetually available and can't be protected when it's not in use. It's basically always in use. And lastly, another reality of the symmetric key encryption algorithms, such as AES, that all full disk encryption solutions use, is that you don't necessarily have to get to the entire key to break the security of the system. So if encryption is in progress and you're able to get to some of the intermediate data that is in the process of being encrypted, or portions of the key that are known as round keys, you can use that information to extrapolate values of full keys. So the moral of this story is that you can't somehow protect keys in a way where you just limit their exposure over the course of the encryption routine. If there's a snapshot taken by an attacker at any point during encryption, they're going to be able to use that information to extrapolate the value of the key. So these are our design constraints, and we have to think about all these problems when we're developing this most comprehensive solution. So we call this a virtual secure enclave, and we like to think of it as essentially a virtual piece of hardware that's inserted into your device using special cryptographic techniques, interacting with the operating system in a particular way, and also taking advantage of some underutilized portions of a Pentium processor. We're able to effectively protect keys as if a piece of dedicated hardware were there to do this for us. And it has three design principles. The first is that long-term disk key data is going to effectively be protected using a key that is distributed over very large regions of DRAM. And we have a way to guarantee that the data remains protected so long as there are a few bit flips per million. Short-term key data as well. So if you reconstruct a key to actually perform the encryption, we have to protect this in a particular way such that the plaintext values of the key aren't ever floating around in memory to encrypt, say, a 128-bit plaintext block. Instead, we can protect these keys within the processor itself and guarantee that that information never actually leaks out to a data cache or to DRAM. And we'll talk about how we do that. And lastly, as part of that protection of the data within the processor, we have to guarantee that the processor doesn't force us to spill that information out to memory at any given time, and we have to take some special steps to ensure that that will be the case. Okay. So first, let's talk about how we protect the long-term disk data with this information that's distributed over very large regions of RAM. Okay, so I won't step through this entire block diagram. I'll touch on just a few portions. But effectively, in our defense system, we're going to be creating a very large DRAM buffer that's randomly generated, and it's large on the order of, say, 1 megabyte. So every time that a full disk encryption solution would invoke an encryption or decryption routine, we would somehow take that information and pass that through a cryptographically secure hash function to reconstruct the key in real time, and then pull some other information that essentially represents, say, the encrypted disk encryption keys from memory, combine that with the hash result to make the disk encryption keys available to decrypt a block. So we have to do this every time we see a read or a write, which can be as small as, say, 1 sector, but it's typically about 4 kilobytes worth of data. So the Princeton paper touches on this. They use actually a concept that's in the research literature known as the exposure resilient functions. But it turns out that the technique that they use might be able to work for, say, a simplistic file encryption system. But for full disk encryption, it's not possible to use that technique to efficiently compute that hash result every single time you want to do a read or a write. In the course of a second, you could be talking about millions of reads and writes that course of a minute, millions of reads or writes that are happening that are going to the underlying file system. So if you're doing something like an SHA 256 hash over a megabyte of memory for every single 512 bytes of data you want to read or write, of course, the performance is not going to be there. It's going to be completely unusable. So we have to engineer some alternatives using smart cryptography that allows us to perform this hashing operation with very few instructions, on the order of thousands or maybe low tens of thousands per invocation. And if we're careful how we do this, we can guarantee in a cryptographic sense that the probability is negligible that someone could brute force that hash result if they grab memory. So effectively, if you're an attacker, and let's just say you perform a cold boot attack and you're able to access whatever's left in this DRAM buffer, even if there are a few bits that are flipped, you're not going to be able to use a brute force attack to compute a new hash result that could be used to derive the disk encryption key. Certainly considerations we have to explore with respect to how big the DRAM buffer has to be given the probability of bits flipping. And we're not going to get into the details of how we make this work. There's certainly different ways you can implement this, but just to kind of give you a high-level sense of how we're thinking about it, essentially there's some number of flips, say F flips, that we can expect to occur over some region of RAM. So let's just say we're using a 1,000,000-bit buffer. Our empirical results showed us that we could expect something on the order of 375 bits to flip. But we tried to aggregate these bit flips very efficiently, much more efficiently than, say, something like a SHA hash, by just performing XOR operations or checksum operations. This can be further accelerated if you employ special instructions to do this quickly within the processor. And then we use a set of very carefully selected nonlinear mixing functions to combine these results to get our hash result in a way that would require exponential effort on the behalf of the attacker to somehow recompute that hash result given a few bit flips occurring. Okay, so we've got to that part. We figured out a way to use this DRAM buffer to take advantage of bit flip so that we can reconstruct a key very quickly and in a very secure way. Now the problem is, once that key is reconstructed, and just popping back to this diagram, you see that the end result is your actual disk decryption key. Well, of course, we don't want to store that in a cache or RAM because if the cold boot attack occurs, they're going to be able to get to that despite what we're doing with the DRAM buffer. So we use some special techniques with Pentium processors to protect these key bits. To describe how we're going to do that, I'm just going to give you a little bit of background on the architecture of a Pentium processor, and there are analogs of this architecture in pretty much every modern microarchitecture that you see. But essentially, the processor is unified with the memory. So DRAM information is moving to and from the processor, and it usually passes through some number of levels of data cache that are on the processor die. For encryption, for most software implementations, what you have is information associated with the keys and the information that you want to protect moving in and out of the processor to and from memory. And then there are instructions that are executed by the core of the processor to perform functions that can be as simple as just adding two numbers together or jumping to a new line in the program. But these operations consume these bits and generate new ones to perform the encryption operation. So the problem here is that even if we were trying to securely deposit somehow the key result in registers, which isn't easy to do, typically an encryption implementation is going to spill this stuff out to memory anyway. So you can think of that stuff on the left, that integer and memory processing unit, as being kind of the reptilian subbrain of a modern Pentium processor. That stuff's been around since the 1970s. But during the 1990s, the processor started to be expanded to support high performance for multimedia applications. So, for example, viewing an MPEG in real time. And they did this by implementing in Pentium processors. You may have heard of extensions such as MMX and SSE. And for the processor to make this work, they had to add storage for processor registers, you can think of as local memory, as well as instructions to operate on these registers. So not that many people use this stuff. It's somewhat esoteric, and you can use it for high-performance applications. But in terms of cryptographic acceleration, and in our case a cold boot defense, we can use it to great effect. So the idea here is we're going to use that MMX and SSE capability, particularly the registers, to store all of the disk encryption keys in the processor such that they would never be spilled to memory. Benefits of this is that the registers themselves are relatively volatile, so the memory is going to go away when the processor is turned off, and it's not going to be susceptible to the cold boot attack scenario. We'll take questions at the end. It also permits a much faster encryption implementation. These MMX operations can operate over things like 128-bit values instead of 32 bits. So it's actually possible for a cold boot attack defense to accelerate full disk encryption. And we kind of got lucky with the number of MMX registers available. In fact, extremely lucky. Turns out that there is almost precisely enough space to store an AES 128 expanded key. And we actually have only one register to spare. So thank you, Intel. But in terms of annoyance, though, it turns out because you have these constraints with number of registers available and the fact that the instruction set is somewhat difficult to use, you have to be very careful and actually have to hand code assembly to make this work. This isn't a C implementation. And also, we have to be a little bit creative with the crypto that we use actually to do decryption to make sure that we don't accidentally let stuff leak out to memory. So the result is that all that information associated with intermediate values and cryptographic keys is kept safely within the core of the processor, never written to a data cache, never written to DRAM when it's in use. Okay, the last piece of this is that our solution protects this stuff within the processor itself, as if we had virtual hardware there. But there are some cases where an operating system is going to force the Pentium to dump all of its contents. It's known as preemptive context switching. So this is a very important feature for general-purpose computers. Preemptive context switching allows you to read your email on your laptop while you're using Microsoft Word to write a summary of the Black Hat conference. Allows you to jump between different applications without you noticing. So it's good for usability, bad for cold boot attack defense. because at any time the operating system can tell the processor to dump the contents of registers to memory for intermediate storage. Of course, we don't want that to happen because that, for us, is sensitive key values. Luckily, there is a way to prevent this from happening. So we use an easy-to-use operating system mechanism to, in the case where our software is invoked to do encryption, we elevate the thread priority. So essentially, we take control of the machine in a way where the operating system can't boot us, even if it wants to. It turns out that the amount of data that we would be processing is relatively small. I mean, again, we're only talking about potentially 4 kilobytes at a time. So we don't hog the processor for too long in a way that would lead to a blue screen or lead to some sort of usability issue. And we verified this empirically. So essentially, when we enter, and it's time for us to do decryption, we grab the processor, elevate our thread priority to highest, then step through the process of computing the disk encryption key by hashing that huge amount of DRAM and efficiently computing the key, performing the encrypted disk I/O with information that's stored and protected within the processor, and then when we're done, we wipe the registers, clean up, and then relinquish the thread priority back to the OS. And it works great. One last point on performance. So depending on the security, how comfortable you are with the security of the system and some of the other trade-offs that you may want to accept in terms of usability and performance, the performance of these defenses can vary. But this is an illustration of one way that we configured the system, where we use a 1 megabyte buffer to distribute memory. I guess with this approach, we demonstrated that if there are as few as 15 flips per million, that we can effectively protect cryptographic keys against any cold boot attack while only incurring a 7% overhead or 7% performance degradation. And that's only in really I/O-intensive processes such as booting. When a user is basically normally interacting with the system by doing something like writing something in Microsoft Word, there's basically negligible performance impact at all. And this graph here kind of demonstrates one way to think of it in terms of the performance impact versus work required by an attacker to pull off a cold boot attack. The red dot represents existing FDE systems where don't introduce any additional performance overhead because they're not using any defenses. And the attacker is required to perform something on the order of 2 to the 32nd operations in order to brute force the keys. In our case, we're actually requiring the attacker to perform 2 to the 80th operations in order to recover the keys, which is simply not feasible given all computers on the planet and given 1,000 years of time. So we move effectively by only incurring a 7% performance impact, move from tractable to intractable, and we can prevent cold boot attacks. Okay, to summarize right before I take some questions. Cold boot attacks are very real. As we've demonstrated, they're easy to pull off in a matter of seconds with basically zero technical expertise. And although there haven't been any reports in the media of them actually occurring, we think that it's only a matter of time before we do hear about them. Why not take a more proactive approach now and using software, no additional hardware or no significant system upgrades, install some protection against cold boot attacks before it becomes a bigger problem? Again, that's just a recap. We showed that we could prevent all these attacks using software-only defenses. But thinking towards the future, it's going to be a matter of time before somebody finds another significant vulnerability in these commodity encryption systems. And we need to start thinking ahead architecturally about things that we can do to prevent them. There's certainly lots of interesting things we can do in the operating system and in application software. But the real solution lies in adding special capability in the hardware itself. As we've demonstrated, just by having a little additional storage within a Pentium processor, we can do some pretty cool things. By thinking more about expanding things like TPM, that the processor vendors are all working on different encryption add-ons to their chips. But there's a lot more we can do to create a more secure future for all of us. So more information is available on our website, bitarmor.com/coldboot, and we'll be around now and after the conference if you have any questions. So thank you very much for your time. Appreciate it. So we'll take questions now.
I was just curious, if you're using the micropurpose registers, how does that affect other applications that may also be using them?
Who wants to me? Okay, so the question is, we're using the MMX registers. Somebody else might be using the MMX registers. How does that affect them? Well, the good news is because we're at the high IRQL, nobody can kick us out of memory anyway, so by the time they're using them, their versions get restored. It doesn't really matter. We happen to have a FDE product of our own, so we were in a very good position to be looking at this stuff. Do you want to say something?
It is in the product that we offer today.
I may have missed it, but why not just use the on-drive solutions that are starting to be offered by Seagate and other people like that?
Do you want to take this, or do
you want it?
Certainly, hardware-based defenses can provide significant protection against these attacks, but you do have to assume that all the laptops and desktops in your enterprise have that hardware in place. So, over the course of the next 5 to 10 years, those sort of technologies will become more pervasive. But in the short term, today, if you want to prevent your enterprise against cold boot attacks, you're not going to upgrade all of your hard drives and implement that management system. So, software is probably the way to go.
One more thing. There is also the advantage. People often talk about software versus hardware on encryption, and that as security technologies mature, they eventually always end up in hardware, and therefore we shouldn't be implementing them in software. Some stuff like this, on the other hand, software does have its advantages. It's more flexible. We have a software solution here. We can fix things when it breaks. If you have hardware out there in the field and somebody finds vulnerability, you have less flexibility in order to move to a new system. So, there are trade-offs.
Can you speak up a little bit? We can't hear you. Can you speak up a little bit?
On your BIOS defense, you put the keys in the same place that the BIOS will copy the boot sector. Yeah. What if the attacker just swaps the DIMMs over in the machine?
Yeah, I think I actually mentioned that. That's actually that's one of the limitations of that defense. If you do swap the DIMMs, you get around it. The interesting thing, though, is that's forcing you to pull the DIMMs out of the sockets and move them. So that means that you're going to have at least some bit flips because of the fact that your memory is going to be without power while you're moving them. So if you're just using the BIOS defense, yeah, all they have to do is swap the DIMMs. If you're using this last defense in addition, well, as you swap the DIMMs, you get a couple bit flips, key gets destroyed.
Okay, cool.
The answer is no, and it's an interesting concern. The very basic things about the decay characteristics of DIMMs have not been explored. There's a lot of things that should be explored in order to figure out what's going on here.
Can we use these ideas without regard to worrying about patents?
There are patents pending on some aspects of this. We can talk to you more about that offline if you're curious. Not all of it. And add something else to the DIMM issue. I guess that's effectively an attack that's slightly out of scope with the cold boot paper, but to design a defense on the fly, I guess you could randomly choose a random location for the encryption key every single time to try to defend against that. But if you're not employing, I guess with several of these techniques, not employing system where you're putting the key in memory anyway, you might be protected. Okay, so would you take one last question? Is that all right? All right, one last question. We'll stay up here if anybody wants any.
Great talk. I enjoyed it very much.
Thanks.
Concerning the temperature probe, I was wondering if you did any experiments trying to keep the temperature probe warm by heating it with a heated probe.
Okay, so we have not tried to keep it running with the heating source applied. The problem with this approach, we haven't tried. The reason why we haven't tried is because the heat sensor is infused in the motherboard, so there is really difficult to get to the sensor with the probe at that point. In addition to this, the sensor may not be accessible as it's underneath another piece of hardware, another piece of board. So getting there with the probe is in many cases difficult.
Okay.
Okay, thank you very much.